An operating system is ultimately an abstraction layer built on top of lifeless hardware. Before it can manage memory or execute programs, it must capture control of the CPU through a strict, deliberate sequence. When the machine powers on, the hardware's internal basic input-output system, or BIOS, runs its initial diagnostics. But the BIOS isn't the operating system. Its primary job is simply to find a specific sector on the storage drive, load a Stage 2 bootloader, like GRUB, and step aside. The bootloader now holds control, and it needs to find the kernel. To ensure it doesn't execute random data, it follows the multi-boot specification. It scans the first 8 kilobytes of the kernel binary, looking for a highly specific 32-bit magic number, 0x1BAB-B002. Once it identifies that signature, it verifies the kernel is valid. With the kernel validated, the bootloader parses its internal structure. The kernel is compiled into an executable and linkable format, or ELF file. By reading the ELF headers, the bootloader determines exactly how the executable code and data must be arranged in memory. However, the lowest portions of physical RAM are heavily restricted, occupied by the BIOS itself, memory-mapped hardware, and the bootloader. To avoid catastrophic collisions, the kernel's linker script explicitly instructs the bootloader to load the code starting at physical address 0x00100000, exactly at the 1 megabyte mark. The multi-boot handoff guarantees that our executable is safely parked in unobstructed memory, and the CPU's instruction pointer is finally handed over to our code. Achieving this execution control is the strict prerequisite to building the rest of the architecture. At this point, the kernel is executing pure assembly code. To write the complex logic of an operating system, we need to transition to a higher-level language like C. But C cannot function in a vacuum. It absolutely requires a functional memory stack to manage local variables and function calls. Because no stack exists yet, our entry assembly file must manually reserve a block of uninitialized memory for this exact purpose. We define a 4 kilobyte chunk of memory within the .bss section of the ELF file. We use the BSS section specifically because it allocates uninitialized space at runtime without bloating the actual file size of the compiled kernel on disk. On the x86 architecture, the stack grows downward toward lower memory addresses. To initialize it, the assembly code points the stack pointer register, ESP, to the very end, the highest logical address of that 4 kilobyte partition. If we need to pass parameters into our C code, such as the multi-boot information structure, we follow the CDEC calling convention. The assembly pushes those arguments onto our newly created stack in a right-to-left order. With the memory primed and the parameters loaded, a single assembly call instruction executes the jump into our primary C function, kmain. By deliberately architecting the stack and making the jump, the kernel escapes the strict limits of raw assembly. It now controls a structured C programming runtime, ready to interface with the physical machine. A kernel that only performs math in RAM is useless. To be an operating system, it must assert physical control over the machine's peripherals, and it does this through 2 distinct architectural pathways. The first pathway is memory-mapped I/O. In this model, writing directly to specific system RAM addresses physically alters hardware states. The primary example is the VGA frame buffer, hardwired to address 0x00B8000. Hardware expects 16-bit memory cells, 8 bits for ASCII, 4 for background, 4 for foreground. In C, we define a struct for this. To prevent invisible compiler padding from causing garbage data, we apply a packed attribute, forcing precise bit alignment. The second hardware pathway operates entirely differently. This is the I/O port system. I/O ports exist outside the standard memory address space. You cannot access them with C pointers. Instead, the CPU has dedicated in and out assembly instructions, which act essentially like sockets to communicate directly with peripheral state machines. Moving the text cursor requires this method. Because the cursor's 16-bit position exceeds the 8-bit data limit of a single port transmission, the kernel must send a byte to a control port at 0x3D4, followed immediately by a byte to the data port at 0x3D5, repeating the sequence for the high and low halves of the position. Memory math I/O and strict I/O port instructions form the low-level read-write vocabulary of the system. They are the mechanisms by which the software kernel dominates the physical hardware. Writing to the screen is entirely dictated by the kernel, but reading input, like from a keyboard, happens asynchronously. If the kernel constantly paused to pull the hardware for updates, the system would freeze. It requires an asynchronous interrupt system. When a physical event occurs, such as a user pressing a key, the keyboard generates a scan code. That electrical signal travels across the motherboard and strikes the Programmable Interrupt Controller, or PIC. By default, the PIC's interrupt offsets overlap with the CPU's internal error exceptions, like divide by zero faults. Before the kernel can safely accept hardware signals, it must send port commands to remap the PIC, moving external interrupts to a safe numerical range. Once properly configured, when the PIC receives that keyboard signal, it fires an interrupt directly into the CPU. The CPU is forced to abruptly suspend its current execution thread, regardless of what code it was running. To ensure the program can resume later, the CPU immediately pushes the instruction pointer, code segment, and flags register onto the stack. It then references the Interrupt Descriptor Table, or IDT, the central routing array dictating which handler function corresponds to the hardware event. The CPU jumps to that handler. Because the CPU only saved a few core registers, the first thing our handler must do is execute an assembly wrapper that pushes all remaining general-purpose registers to the stack. The C code processes the keystroke. The assembly wrapper pops the registers off, executing an IRET to restore the CPU precisely to its previous state. The Programmable Interrupt Controller and the Interrupt Descriptor Table establish a robust, fail-safe pipeline. They grant the kernel the ability to react instantly to chaotic hardware demands without corrupting the execution state of the system. To run user programs securely, the kernel must isolate memory. Without isolation, a poorly written application could overwrite the kernel's data structures, crashing the entire machine. The x86 architecture enforces a mandated layer of memory translation to solve this, known as segmentation. It completely abstracts the raw physical RAM. This diagram maps how a logical address is structured. Whenever the processor accesses memory, it uses a 48-bit logical address. It breaks down into a 16-bit segment selector and a 32-bit offset, which combine to reference the specific segment descriptor. These segment descriptors are stored in a master array created by the kernel called the Global Descriptor Table, or GDT. But GDT explicitly configures the base address and the upper limit size for every active memory segment. Crucially, the GDT embeds a hardware-level security feature, the descriptor privilege level. It strictly divides execution into protection rings, ensuring code running in Ring 3, user space, is structurally blocked from accessing segments designated for Ring 0, the kernel. While the GDT successfully enforces these security rings at the hardware level, segmentation requires large, contiguous blocks of physical memory. It is far too rigid to handle dynamic application environments efficiently, requiring a second, finer layer of virtualization. That second layer is paging. Paging translates the linear addresses produced by the segmentation process into absolute physical memory page frames, completely divorcing an application's concept of memory from the physical reality of the silicon. This schematic shows how the memory management unit slices a 32-bit linear address. The highest 10 bits indicate an offset within a page directory, the next 10 locate an entry within a page table, and the final 12 define the exact offset inside the frame. The MMU resolves this by looking at the CR3 register to find the base physical address of the page directory. It uses the first 10 bits to find the specific page table and the next 10 bits to locate the exact physical frame. Finally, the lowest 12-bit offset targets the exact byte within that 4096-byte physical page frame. Paging enables a powerful architectural design pattern known as the higher half kernel. Because the page tables dictate where virtual addresses point physically, we can map the kernel's actual location in physical RAM up to the extremely high virtual address 0xC0000000, the 3 GB mark. By shifting the kernel entirely into the higher half of the virtual space, the lower address space is left completely empty. This spatial logic is critical. It allows standard user applications to be blindly loaded and linked to virtual address 0. They have 3 GB of continuous, isolated virtual space to operate in without ever risking a collision with the kernel's data structures. By layering the multi-boot loading standards, strict hardware I/O control, an IDT-managed interrupt pipeline, and MMU-enforced memory paging, the operating system is structurally complete. The bare metal has been transformed into a secure, highly abstracted execution environment.